Hello and welcome. My name is Brandon Chavez. Today we're going to talk about Amazon EC2 instances that are powered by the AWS Graviton2 processors. To set a little bit of context, AWS has the broadest and deepest range of choices for compute in the cloud. We have families of instances designed for virtually any workload, whether you want to optimize for raw CPU cycles, memory per CPU, even high I/O storage and powerful GPUs. There is an instance category to meet your needs. And each of these instance categories can be further customized, including with the choice of processor, the type of storage, things like ultra high-speed networking, and even bare metal options. You can add in other options such as Elastic Block Store, and we have over 400 distinct instance types, giving our customers the most choice and flexibility when it comes to compute. Amazon EC2 also has the broadest choice of processors, including a full range of Intel Xeon processors. We also leverage the EPYC processors from AMD, which is a powerful but cost-effective option for x86 workloads. And finally, we have our own custom-designed and built processors, the AWS Graviton family. And today, as mentioned, we're going to dive a bit deeper into Graviton, so let's get started. So the AWS Graviton processors are completely custom designed by Annapurna Labs around the 64-bit ARM Neoverse N1 core. With our vast experience here at AWS in running cloud-native workloads at scale, we've been able to target specific optimizations in this processor itself. So Graviton is literally designed for the cloud. By building our own custom processors, we can rapidly innovate and iterate on behalf of our customers, providing great performance with significant cost savings. After the first generation Graviton-powered instance, the A1, we wanted to really broaden the workloads and target applications for the Graviton processor line. Workloads we especially wanted to focus on include high-performance computing, media encoding, in-memory caches, even the electronic design automation we ourselves use to design the processors. These additional workloads pushed us to keep innovating, and at reInvent 2019, 1 year after the first generation Graviton processors, we announced the AWS Graviton2 processors, which are significantly more powerful and suited to a much wider set of workloads. And here in this slide, we have Andy Jassy on stage at reInvent 2019 announcing the Graviton2 powered new M6g, R6g, and C6g instances. And we'll talk more about the specific instance families in a bit, but first let's get a look at the Graviton2 processor. So here's an actual photo of the new Graviton processor, the AWS Graviton2 processor rather. It has 64-bit ARM Neoverse N1 cores, roughly 30 billion transistors, and it's the first 7nm processor deployed at AWS. And compared to the first generation of Graviton, Graviton 2 has 7 times the performance, 4 times the number of cores, 5 times faster memory, and twice the total amount of cache. And it really delivers some tremendous performance. So let's look at where we're utilizing this processor in our actual EC2 instances today. We're able to offer the AWS Graviton2 processor across 6 different instance types. All of these Graviton2-based instances offer up to 40% better priced performance when compared to similar x86-based instances. So we have the M6g, which is suitable for general purpose workloads like the rest of the M series of instances. We have the C6g for compute intensive workloads and the R6g for memory intensive workloads. We also have the T4G, which is suitable for burstable general purpose workloads, which is available for a free trial. The C6GN, which recently launched at reInvent 2020, which is suitable for compute intensive workloads, but also provides enhanced networking and EBS bandwidth. And then we have the very recently launched X2GD, which provides the highest ratio of memory to CPU within the Graviton family, and also comes both storage and networking optimized by default. And then across these instance types, say for the T family, you can also get an NVMe-based storage option. So that would be the M6GD, the C6GD, and then the R6GD. And of course, as mentioned, the X2 comes with NVMe-based SSD storage by default. And then again, for all of these instance types, except for the T, you can also get a bare metal option. So the M6g.metal, M6gd.metal, and so on. The metal suffix makes it pretty straightforward what you're getting there. So really quickly, we can just sort of look at the instance families here. The M6g, the thing to note about the M series instances is that there's a 1:4 ratio of CPU to memory. So you'll see how the memory and CPU ratios vary between instance families, but scale consistently within a family. And you can see the M6G goes up to 64 CPUs and 256 gigs of memory. Something to note about the Graviton instance families as well is that every vCPU that you get in the instance is a dedicated core and not a hyperthread like you might find on Intel-powered instances. Moving to our compute-optimized C6G, you'll see here the ratio of CPU to memory is 1:2, meaning that the largest size here, the C6G 16XL, has again 64 vCPUs, each one a physical core, and 128 gigs of memory. And then looking at the R6G, the memory-optimized variant, for every one vCPU, you get 8 gigs of memory, leading to a largest instance size of the R6G 16XL providing 64 vCPUs and 512 gigs of memory. And so looking at the X2GD in detail, you can see that this instance type provides a 1:16 ratio of CPU to memory, includes the local NVMe SSD instance storage up to two 1.9 terabyte SSDs, and is network and EBS bandwidth optimized. The largest size here will get you 64 cores of Graviton CPU and over a terabyte of memory. And here on this slide, we are giving you a comparison of the instance storage availability across these different D variant instance types. So again, remember that D connotates the disk variants having the local NVMe SSD storage here. You can see that across the instance sizes, there are variances in memory to CPU ratio, but you get fairly consistent progression of SSD storage additions up across the instance families. So going from a single 59 gig NVMe SSD in the dot mediums up to the 16XLs, bringing you two 1.9 terabyte NVMe SSDs available locally in the instance. Looking at the T4G, you'll see that the T4G goes up to 2XL, giving you the option of consuming up to 8 vCPUs and 32 gigs of memory. And there are variances in how much burstable performance is available and how quickly you regain CPU credits across the T instance family. Then finally, last but not least, the C6GN, the recently announced high network bandwidth and high EBS bandwidth variant of our compute-optimized C6G instance. This again has the same ratio of CPU to memory, but the important variations here are that all of these C6GN instances offer high memory bandwidth, high network bandwidth and high EBS bandwidth for highly performant storage use cases. So let's get a little bit more granular and take a look at what makes up each Graviton2 instance. So first we have the Graviton2 processor itself, which we've introduced as a 7 nanometer piece of custom silicon that offers exceptional performance. But Graviton2 isn't the only piece of custom hardware powering Amazon EC2. So there's also the Nitro security chip, which is integrated into the motherboard of each server and protects and monitors hardware resources. And the Nitro card itself unloads many of the traditional software needs of the hypervisor into bespoke hardware, allowing for much better performance with a much lighter footprint. So the Nitro card handles interfacing with devices such as Amazon EBS or Amazon ENA, and also provides additional monitoring and security for those interfaces. And finally, because of the Nitro security chip and the Nitro card, the Nitro hypervisor itself is very lightweight, and it handles CPU and memory allocation with bare metal-like performance. And these are, of course, all exclusive to Amazon EC2. So one of the most important things we like to talk about when it comes to Graviton 2 is how they can help lower your total cost of ownership significantly. So remember, the Graviton processors, the Graviton 2 powered instances, have the highest performance within their instance families, along with, on average, about 20% lower cost when compared with the other instances in the same family. So when you start to stack these performance gains with these cost savings, you can see up to 40% better price performance or reduction in TCO versus comparable x86 instances. So this is the best price to performance within instance families and really can lead to significant savings for our customers. Because of these amazing price to performance benefits, we're also making sure that Graviton powered instances are consumable across a wide range of AWS services. So for example, Amazon ElastiCache offers M6g and R6g Graviton2-based instances for Redis and Memcached. For some of these workloads, we see up to a 45% price to performance improvement over the previous generation instances. And we believe that this is the right choice for our customers, so in ElastiCache, Graviton 2 is now the default choice for instances. We've also added Graviton 2 powered instances to RDS, where we can see up to 35% performance improvements and up to 52% price to performance improvements for the open source databases in RDS. And of course, this does vary depending on the database engine or version and the workload shape, but in general, the performance gains that we observe in RDS are fairly consistent and very impressive. Should you choose to consume databases through Aurora, we just recently made this generally available. And in the context of Aurora, we see up to 20% performance improvements and up to 35% aggregate price to performance improvements, depending on the database size. So definitely worth considering, sort of regardless of the database that you run on AWS, whether it's through Aurora or RDS, Graviton 2 really provides significant performance gains and cost savings for our customers. Elastic MapReduce has also recently added support for Graviton 2 instances. And in the case of Spark workloads, we see up to 35% lower costs and up to 15% improved performance on Graviton 2-based instances. In the case of VMR, there are definitely specific versions that you need to use to make sure that you get those performance optimizations for Graviton 2. But aside from that, it is very straightforward to consume Graviton instances through Elastic MapReduce. AWS Code Build recently introduced support for ARM-based workloads, allowing you to compile code that can run on Graviton 2 instances, making it very easy to adopt the build processes to start taking advantage of Graviton 2 instances by building your code base for ARM64 processor architectures and migrating over to Graviton. So now let's talk about what does the ecosystem support look like for Graviton instances. The net of it is that chances are, if you're using something today, there is support for Graviton. So let's start at the foundations here, looking at operating systems. Across the board, whether you're using Linux or BSD, there's support for Graviton out of the box. The only consideration here is the version of the OS you're using. So looking at Amazon Linux, you need to be on Amazon Linux 2 to ensure you have proper support for Graviton. If you're a Red Hat Enterprise Linux customer, you also want to make sure you're on 8.2 or newer. Ubuntu, similar story, 1804 LTS or 2004 LTS. As of today, Windows is not supported on Graviton, but in the Linux and BSD ecosystem, the support is really out of the box. Getting more granular, looking across the ecosystem, support for Graviton in the container space is quite strong, with Docker itself supporting multi-architecture images, making it very seamless to build and deploy containerized applications to both x86 and ARM64 instances. Our own container orchestration systems, EKS and ECS, have first-class support for Graviton, including things like the ECS and EKS optimized Amazon Linux AMIs. We have them built directly for ARM64, so it's super easy to spin up a Graviton2 powered instance within one of your EKS or ECS clusters. You can even run them side by side with x86 instances, making it very easy to start adding Graviton to your existing container workloads. And then, of course, ECR, the Elastic Container Registry, has support for multi-architecture images, as does Docker Hub, making it extremely easy and straightforward to add an additional architecture to your development workflow. And across the board, in the AWS software ecosystem, Graviton2 support is becoming the standard. So it's really nice to see projects like the Amazon Corretto OpenJDK distribution really packaging all of those Graviton2 performance enhancements right into OpenJDK. And of course, these are in other variants of these performance enhancements are in other versions of the OpenJDK, but Amazon Corretto is where you're going to find those performance optimizations the most rapidly. And then looking across some of the other tools and services in AWS, things like Amazon or AWS autoscaling supports mixed architecture autoscaling groups, making it pretty straightforward to start adding additional Graviton2 capacity into your existing autoscaling groups. The AWS Code suite of services, so code deploy, code build, and code commit, make it very straightforward for you to start adding build pipelines for ARM64 variants of your software. So the support across AWS for Graviton is really first class, and we want to make sure that anywhere you might want to use Graviton or deploy software to a Graviton instance, that support is there and very straightforward to take advantage of. And then zooming out a little bit, looking across the broader software ecosystem, thinking about ISVs and open source projects, the support for ARM64 and thus Graviton2 is quite good. So looking across some of the databases here, it's pretty common to find performance gains across most of these databases when running on Graviton2. Looking at some of the tools you might need in your production stack, whether it's an infrastructure as code tool like Chef or Terraform, or a monitoring tool like Datadog or Honeycomb or Splunk, the support is there, and you can monitor and gather logs from Graviton2 instances using these tools. With security, the story is much the same. Our security partners here, Tenable, Rapid7, CrowdStrike, support running their agents on Graviton2 instances. And then, of course, for the build and test workflow, our CI/CD partners like GitLab and Travis CI have first-class support for building ARM64 applications for Graviton2 instances, as well as deploying to ARM64 systems. So now that we've given you an overview of the Graviton landscape and sort of where you can take advantage of it, whether you're using AWS services or open source software, now let's deep dive into the Graviton2 processor itself and see what makes it such a great value proposition. So we should start with a little bit of history. The first AWS Graviton processor, which powers the A1 instance type, is a 16 nanometer chip with about 5 billion transistors. And the Graviton2 processor has 4 times the number of vCPUs with 7 times the performance, which if you're doing the math is roughly twice the performance per vCPU. And Graviton2 is also the first 7 nanometer chip in EC2. And keep in mind, these pictures are to scale. Graviton2 has around 30 billion transistors overall. And then let's talk a little bit about cores, N1 and ARM 8v2. The N1 core is what powers Graviton2, and there's 64 of them inside each processor. AWS worked closely during development with ARM, combining AWS's experience as the as a cloud vendor, together with ARM's expertise in CPU microarchitecture, to design a processor that was specifically built with cloud workloads and scale-out workloads in mind. One example of designing for cloud-native workloads specifically is a large 64 KB L1 cache and a 1 megabit L2 cache, which is over twice the caching per vCPU as our previous Graviton processor. And one of the most important things to note is that we did talk about this earlier, but every vCPU in a Graviton instance is a physical core. So one of the advantages of having 64 cores per CPU, and there's no SMT in Graviton. Graviton 2 connects those 64 cores together with a mesh interconnect. This gives us approximately 2 terabytes per second in bisection bandwidth. A 32 megabyte LLC allows for over 100 megabytes of user accessible caches. And because of the mesh, there's no NUMA concerns with Graviton 2. Every core sees the same path to memory and other cores. This alone can increase performance on non-NUMA optimized applications pretty significantly. And Graviton 2 also supports 4th generation PCIe, which powers the local NVMe SSD storage available in the D variants. Remember, M6gD, C6gD, and R6gD. So let's take a look at some of the actual performance gains from some of these features that we noted in the Graviton 2 CPU. So let's start with SPEC CPU 2017, which is an industry standard benchmark for CPUs. We use the 2017 variant, which is a few years old, and because of that, it's also fairly stable. It's written in C and C++, and it runs across all of the vCPUs concurrently. It includes a wide variety of benchmarks from Perl, compiling code with GCC, route planning, Sudoku solvers, and a few others. On the floating point side, it also includes things like physics simulations and ray tracing. And so our SPEC scores estimates as much as 44% faster performance than an M5, which is pretty impressive. But it doesn't mean that the performance gains are only restricted to synthetic benchmarks. We also see pretty comparable performance gains when we look at real-world workloads. As an example of a real-world workload, we did some tests with NGINX, which is a popular web server and load balancer, and we used an open source load tester, WRK, which we pronounce work, to generate 512 clients worth of HTTPS requests to send through NGINX. In this test configuration, we saw a 24% increase in requests per second with the M6g, delivering more performance at a lower cost than the comparable M5 instance. We also did some benchmarking with Memcached, which is a key value store that provides a very fast lookup of data. It's often used in front of databases as it can be much faster than the database itself, which generally improves responsiveness for your applications. In this workload, we tested it with 576 load-generating connections, which were requested from 2 C5 9XLs, and we also had a third C5 9XL load generator that was measuring latency. So we compared the performance of an M6g 2XL to an M5 2XL and found the Graviton2-based instance had about 43% more throughput. Now, throughput isn't the end-all be-all of benchmarking, especially for caching layers like Memcached, where latency can actually be the more important metric, because this is what your customers will notice. But what we observed is that the M6G-based instances had lower latency than the M5 pretty much across the board. Another real-world cloud-based workload is video encoding. Video is a huge part of internet traffic, and encoding video is a large portion of many cloud-based compute workloads. For this benchmark, we used X264 to encode an uncompressed 1080p video to H264 which is currently the industry standard for web-based and mobile delivery of video. The M6g instance was 26% faster in terms of frames per second than a similarly sized M5, and again, for less cost per hour. Even in machine learning, we see performance gains from the Graviton2 processor. In this case, we use BERT, which is a state-of-the-art encoder for text and text feature representation. And this is good performance in this particular workload type is crucial for successful machine learning workload performance. The Graviton2 processor has specific instruction sets to support machine learning workload acceleration. In this particular example, the M6g outperforms the M5 in CPU-based inference workloads and demonstrates a 28% lower latency than M5. And finally, my favorite benchmark, this was also benchmarked using SPEC 2017, is the performance per watt metric for the Graviton2-based instances. Here we see the R6G metal demonstrates 3.5 times more performance per watt than the R5 metal. And these efficiency gains mean a few things. This means that we can run Graviton2 powered instances at higher density with less cooling requirements. In general, they consume less power, which leads to two really nice results, which is lower costs, which we pass forward to our customers, and then also a lower carbon footprint. So using Graviton2 instances can actually help you reduce your carbon footprint and help AWS reduce ours as well. So let's look at some feedback for Graviton2 use cases in the real world. KeyDB found the M6g instance to be over twice as cost effective when comparing price to performance. In regards to straight up performance, not just comparing or not including cost in this comparison, the M6g large is 65% faster than the M5 large for less cost. At honeycomb.io, they've been consuming Graviton-powered M6g instances, and they've been moving increasingly more workloads to the Graviton instance family. In the case of their one particular workload using the C6g instances, they were actually able to reduce their overall instance footprint by 35% while serving the same amount of traffic as compared to the C5 instances. And I think this is a really notable example because we see this pattern with customers continuously. The enhanced performance from Graviton can often help you reduce your EC2 footprint, so you can look beyond just the cost savings on a per unit basis. And there's actually multiple levers you can pull to optimize your spend because of the enhanced performance of Graviton2 powered instances. Here's ANANTech, which is a highly respected hardware technical review website. It's been around since 1997. I feel like this is probably where I got some of my start learning about some of this tech. So it's been around for a while. But they reviewed the Graviton2 processor, and in their words, they suggest that AWS has hit it out of the park in terms of value. I do recommend reading the full review on ANANTech. It has a lot of very interesting benchmarks and detailed technical information, but it's super cool to see a publication that I grew up reading talking about the Graviton2 processor. And here's a more condensed view of some additional customer workloads that we've seen on Graviton2. I think as a high-level summary of this slide, it's just interesting to call out that the variety of workloads we see represented here is pretty impressive. And all of these customers are observing performance gains and cost savings, and it is not just restricted to a single type of workload. So looking at the top here at the Domo workload, they're consuming Graviton2 instances through their Kubernetes clusters, and it took them about a month to migrate about 50% of their EC2 footprint. All in all, they were able to reduce their EC2 spend by about 20%, and this is from a combination of the direct cost savings and then performance-enabled scale down. So yet another interesting variation of how you can save money using Graviton 2. In this case, you can consider occasionally going to smaller instances or running less instances to serve the same traffic as you were before. With Nextroll, they observed up to 50% better price performance for their web server and stream processing workloads. SmugMug migrated their PHP-based photo serving application and achieved 40% better price performance, also calling out the need for minimal code changes in that migration. Snapchat is a outspoken Graviton 2 customer here, consuming Graviton 2-based instances through their Amazon Elastic Kubernetes service clusters. So in this case, they were able to actually reduce the size of the Snapchat messaging fleet and save a lot on their EC2 spend from a combination of the per unit savings of Graviton instances, as well as, again, just running less instances to serve the same workloads. Hotel Beds ran their own tests on M6g instances and found up to 43% better price performance over M5. Mobius Space, they containerized some Java workloads and were able to achieve 40% performance improvement and a 20% lower price compared to M5 instances. And Raygun tested their .NET Core workloads at M6g and saw a 30% performance gain over comparable M5 instances. So with all that praise and all those performance gains to be obtained, the next logical thing to think about is how can you take advantage of Graviton 2? So we're going to focus really quickly on some best practices and some workflows and patterns that we've seen help make this transition as seamless as possible. So first, if we think about what's supported on ARM64 today, the reality is it's probably most of the languages and tools that you are currently using. Interpreted and compiled bytecode languages often just work without any modification. So Python, Java, Node.js, and others are abstracted enough to be highly portable across architectures. There are, in some cases, considerations for the specific version of the runtime you're using. For example, JDK 8 supports ARM64, but really the best performance on Graviton can be obtained using JDK 11. For compiled applications, they will need to be recompiled for ARM64, but the good news is every major compiler supports ARM64. And the most popular compiled languages such as C++ and Go all support ARM64 out of the box. For AMIs, the majority of Linux distributions, including BSD variants, have ARM64 versions. And our own AWS tools and SDKs work transparently on Graviton 2-based instances, including things like the AWS CLI and the SSM agent. As mentioned earlier, the container ecosystem on AWS has terrific support for Graviton 2 and ARM64. ECS and EKS both support Graviton 2-based instances as worker nodes. ECR supports multi-architecture manifests, and code build can be leveraged to build container images for both x86 and ARM-based instances in parallel. Docker itself supports a full multiple architecture toolchain through its new Docker buildx command. So, in actually undertaking a migration, the first step to migrate to Graviton 2 is to identify all of your software dependencies in your production environment. This includes standard and open source libraries, any proprietary in-house libraries, and any monitoring, logging, or security agents that you use in production. Once you've inventoried the software environment, which is a good practice even outside of a Graviton 2 migration, check for ARM64 support for each of your dependencies. Many times there will already be existing binaries or Docker images already built for ARM64. If not, the vendor or provider may have ARM64 support on their roadmap. And you can, of course, reach out to your AWS account team to help investigate or escalate on your behalf. You can also reach out to the Graviton team here at AWS through this email address in the case that you find some gap in ARM64 support and you would like our help in remedying. So once you've identified all of your production dependencies and located ARM64 compatible versions of them, the next step is to test. End-to-end testing, including running your unit and integration and acceptance testing, should absolutely be performed. After all the tests come back successful, the next step is to update your deployment tooling. If you're using infrastructure as code like CloudFormation or AWS CDK, you can just modify your templates to provision ARM64 instances, and this is often a very simple modification to make. When your infrastructure as code tooling or other deployment mechanism has been updated, the final step is to deploy a new ARM64-based stack in parallel with your existing x86-based one, and then use weighted routing through either a load balancer such as an ALB or DNS via Route 53, and send a small percentage of traffic to the new ARM64-based stack. Monitor any critical indicators before migrating larger and larger percentages of production traffic over to ARM64. Lastly, a great source of up-to-date and consistently last sort of great up-to-date information on all things Graviton 2 here is our Getting Started guide on github.com. We really make sure to keep this fully current, so for any modifications that we make to ARM64 software out in the ecosystem, you can find records of that on this GitHub repo. If you're looking for things like specific versions of software that have Graviton 2 support or specific compiler flags for your desired compiler to make sure you get the best performance for your application on Graviton 2, this is the place to go. It includes a ton of tips and tricks for really maximizing performance and just optimizing your experience across languages and libraries during a Graviton 2 migration. So let's summarize what we've talked about today. So the new 6th generation instances powered by AWS Graviton 2 processors, the M6g, C6g, R6g, and T4g, provide up to 40% better price performance over comparable x86-based instances. And these instances are also suitable for a very wide range of workloads, including compute-intensive workloads such as high-performance computing and video encoding. Most Linux and open source applications run well on multiple architectures, x86 and ARM, and can run on these new Graviton 2 powered instances. And remember, today Graviton 2 powered instances are supported by most popular Linux distributions and a large ecosystem of ISVs, and Graviton 2 support is just there, right out of the box. And remember, these instances are available now, along with the local NVMe and bare metal variants for you to start using and running your workloads on. So thanks very much for your time today. I hope you've learned a lot and you have an idea of some of the performance and cost savings, performance gains and cost savings that you can obtain from migrating to Graviton 2. And you've also gotten a good idea of what a transition path might look like, how you can start taking advantage of Graviton 2 and migrate workloads over. We invite you to take a look at the Graviton 2 product page for more details on some of the customer references that we included in this presentation, and also to go learn more about Graviton 2 through the EC2 documentation. Thank you very much, and have a nice day.